Starship is the most difficult rocket ever developed. It is the largest rocket, so SpaceX has no prior example to reference. Every system, structure, and process has to be figured out from scratch. Additionally, Starship is fully reusable, meaning both the Super Heavy booster and the upper stage are designed to return to Earth after launch and be used again. SpaceX has made significant progress, but every flight reveals new challenges. Flight 8 was no exception, exposing serious engine issues that need to be addressed. In today's video, we will break down these problems and SpaceX's approach to solving them. Before we dive deeper, please subscribe to our channel for future updates on Starship and SpaceX's latest advancements. Flight 8 launched from SpaceX's Boca, Chica facility in Texas on March 7th. The launch started smoothly, with all 33 Raptor engines on the Super Heavy booster igniting and lifting the vehicle off the pad. As the rocket climbed, it performed as expected, reaching stage separation using the hot staging process. At this point, problems began to emerge. Starship's second stage engines ignited, but small fires broke out near the vacuum engines. Over time, multiple engines failed mid-flight due to leaks in the sea-level engines. Despite these problems, the vehicle continued its trajectory, collecting data before ultimately losing control due to an imbalance in thrust caused by engine failures. Meanwhile, Super Heavy executed its boost-back burn and began descending toward the Gulf of Mexico for landing. During the landing burn, only one of the three engines reignited, showing that the other two had failed. However, the booster still managed a controlled splashdown, showing improvements in reusability. Cameras at the launch site captured the descent, confirming that the booster's guidance and control systems worked well. Starship, on the other hand, continued to struggle with engine failures until it lost stability and broke apart before completing its mission. This loss of control pointed to serious issues with thrust vectoring and engine reliability. The flight provided important engineering data, but also highlighted how much work remains before Starship can be fully reusable. Post-flight analysis also found damage at the launch site, with ground support equipment scattered due to the extreme forces during takeoff. One of the biggest problems during the recent test flight was the multiple engine failures affecting both Super Heavy and Starship. The Super Heavy booster was supposed to use 3 Raptor engines for the boost-back and landing burn to slow down for a controlled descent. However, only one engine successfully reignited, while the other 2 failed. This resulted in an uncontrolled approach, but the booster still managed to execute a stable splashdown. While the landing was a partial success, the failure of 2 engines highlighted serious reliability issues that need to be addressed. In future flights, SpaceX plans to catch the booster with the launch tower's mechanical arms, which will require all necessary engines to function correctly for a precision landing. The exact cause of these engine failures is under investigation, but previous flights have shown that igniter reliability, fuel supply inconsistencies, and combustion stability are common failure points. Additionally, Raptor engines experience extreme thermal and pressure changes, particularly during multiple ignition cycles in flight. If the igniters or fuel pumps do not operate as expected, the engines may fail to restart, leading to a loss of thrust. SpaceX needs to refine these systems to improve the booster's ability to land reliably. Starship itself had even more serious problems. Shortly after stage separation, the upper stage ignited its 6 Raptor engines, but multiple failures began to occur. Fires broke out near the vacuum engines, and leaks in the sea-level engines led to shutdowns. Over time, these failures escalated, leaving only 2 vacuum engines operational. This created an imbalance in thrust, making it impossible for the vehicle to maintain control. Eventually, Starship lost stability and was destroyed before completing its mission. One of the major contributing factors to these failures was excessive vibrations, also known as harmonic resonance. Starship's structure is exposed to intense vibrations from the Raptor engines, and if certain sections of the vehicle are not properly reinforced, these vibrations can cause leaks, cracks, and structural damage. The leaks in the engine section likely worsened due to these vibrations, leading to a loss of propellant and onboard fires. This issue was also seen in Flight 7, which suggests that SpaceX needs to improve Starship's structural damping and fuel system reliability. Another key issue is Starship's heat shield and tank pressurization system. The heat shield is critical for protecting the vehicle during re-entry, but if leaks and fires continue to occur in flight, they could weaken the protective tiles. This could lead to more severe damage during re-entry, potentially compromising the entire vehicle. Similarly, pressurization issues in the propellant tanks can affect fuel flow, leading to uneven combustion and unexpected engine shutdowns. These systems need to be further refined to ensure that Starship can complete both ascent and re-entry safely. The launch site also sustained damage during Flight 8. Photos taken after the launch showed that ground equipment was displaced due to the extreme forces from liftoff. The orbital launch mount, which holds the rocket before liftoff, experienced high stress, and some smaller structures were damaged or knocked loose. Cameras placed around the pad were also affected. Although the water deluge system helped reduce some of the stress from launch, it may need further upgrades to better protect the ground infrastructure. If SpaceX wants to increase the launch cadence, improving the durability of the launch pad will be essential. There were also problems before the launch. On March 3rd, SpaceX attempted to launch but had to scrub the mission due to a fuel pump system failure in the Super Heavy booster. The issue prevented the engines from generating enough pressure to ignite. This raised concerns about the reliability of the fueling system, which must work consistently if SpaceX wants to operate Starship efficiently. The fueling process needs to be refined to prevent similar failures in the future. Another issue involved the hot staging system, which allows Starship to separate from Super Heavy while its engines are already firing. The system faced difficulties, possibly due to a problem in the liquid oxygen tank. If the tank pressurization is not properly managed, it can cause unexpected pressure drops or leaks, affecting the stage separation process. Since hot staging is critical for improving Starship's performance, these problems must be addressed before future flights. Since Flight 8 experienced a low-power igniter system problem, which led to engine failures, SpaceX is likely working on improving the igniter system to ensure reliable engine startups. This includes reinforcing the igniters and adding protective measures to prevent leaks or fuel system malfunctions. A long-term solution to engine reliability is transitioning to Raptor 3 engines. Raptor 3, introduced last year, is more powerful and efficient than previous versions. Its design eliminates many small components that have caused failures in earlier flights. This should help reduce ignition failures and unexpected shutdowns. Currently, Super Heavy still uses Raptor 1 engines, but SpaceX may accelerate the transition to Raptor 3 for testing. If these engines prove to be more reliable, they will likely be used on all future Starship flights. To fix Starship's fuel leaks and fires, SpaceX is expected to improve the venting and nitrogen purge systems. These systems regulate pressure inside the tanks and engines, preventing unstable combustion. Vibrations have also been a challenge for other rockets, such as the Soviet N-1, which failed due to extreme structural vibrations that led to fuel line failures and engine explosions. Learning from these failures, later rockets incorporated better damping systems to handle vibrations during flight. That's it for today's video. Thanks for watching, and see you in the next one.